Before the jet engine, the sky was already conquered, but only within limits. Aviation had proven its worth in war, exploration, and commerce. Yet it remained bound to a mechanical principle that had changed little since the earliest days of flight. The propeller, elegant and reliable, had carried humanity across oceans and continents. But by the late 1930s, it had begun to reveal an unavoidable truth. It could not take aviation much further. As aircraft flew faster, the tips of propeller blades approached the speed of sound, creating shock waves, violent vibrations, and a sudden collapse in efficiency. Engineers found themselves fighting physics itself. No matter how powerful the piston engines became, no matter how refined the airframes were, speed increases grew marginal, fuel consumption soared, and structural stresses multiplied. At the same time, the world was accelerating. Political tensions were rising, global trade was expanding, and distance was no longer an inconvenience. It was a strategic obstacle. Militaries needed aircraft that could climb higher, fly faster, and outrun defenses that were rapidly improving. Civil aviation faced its own pressure. Airlines envisioned a future where intercontinental travel was not a grueling endurance test, but a routine experience measured in hours rather than days. The problem was no longer whether humans could fly. The problem was how far, how fast, and how efficiently they could do it. This was not a challenge that incremental improvements could solve. It required a fundamental rethinking of how thrust itself was generated. Instead of pulling an aircraft through the air with spinning blades, a radical idea resurfaced. What if air could be drawn in, compressed, mixed with fuel, ignited, and expelled rearward in a continuous stream, producing thrust by pure reaction? The physics were well understood on paper. The practical execution was something else entirely. In Britain, a young Royal Air Force officer named Frank Whittle was among the first to see that the future of flight lay beyond the propeller. Trained as a pilot, but gifted as an engineer, Whittle recognized that gas turbine technology, already used in limited industrial applications, could be adapted to aviation. His vision was audacious: an engine with no pistons, no crankshafts, and no propeller, relying instead on continuous combustion and rotational compression to generate thrust. It was a concept decades ahead of the materials, manufacturing techniques, and institutional mindset of its time. Almost simultaneously, and entirely independently, Hans von Ohain was pursuing a similar path in Germany. Where Whittle was driven by operational necessity, von Ohain was guided by theoretical clarity. His work focused on simplifying the thermodynamic cycle, proving that a compact, lightweight turbojet could function reliably enough to power an aircraft. The convergence of these two efforts was not collaboration, but inevitability. The problem was universal. The solution could only be delayed, not avoided. Yet belief in the jet engine was scarce. Governments were skeptical. Aircraft manufacturers were cautious. The risks were enormous. Early turbojets suffered from extreme temperatures, inefficient compressors, and catastrophic material failures. Turbine blades cracked, combustion chambers overheated, and engines failed without warning. Developing a jet engine demanded unprecedented precision in metallurgy, airflow management, and thermal control. Every component operated at the edge of known engineering limits. Financially, the gamble was just as severe. Funding a technology that had no proven commercial application during wartime required faith bordering on recklessness. In Britain, Whittle struggled for years to secure consistent backing, fighting bureaucratic inertia and technical doubt. In Germany, jet development was supported more aggressively, but under immense political pressure to deliver immediate military results. Failure was not merely professional. It could be fatal. The breakthrough came not in perfection, but in sufficiency. Early jet engines were inefficient, fuel-hungry, and unreliable by modern standards. Yet, they demonstrated something revolutionary. Sustained, jet-powered flight was possible. When the first jet aircraft lifted off, the implications were immediate and unmistakable. These machines climbed faster, flew higher, and reached speeds that propeller-driven aircraft could not safely approach. The atmosphere itself became a different medium at these altitudes, thinner, colder, and more forgiving to high-speed flight. For pilots, the experience was transformative. The vibration and mechanical complexity of piston engines gave way to a smooth, continuous thrust. For designers, new freedoms emerged. Aircraft no longer needed large propeller clearances or massive engine nacelles dominating the nose. Wings could be swept, fuselages streamlined, and speed prioritized without compromise. The jet engine did not merely enhance aviation, it rewrote its design language. The impact extended far beyond the cockpit. Airlines quickly recognized that jet propulsion would redefine economics. Faster aircraft meant higher utilization rates, shorter travel times, and entirely new route structures. Cities once separated by oceans became connected by schedules. The jet age collapsed geography, turning distant nations into neighbors and accelerating globalization decades ahead of its time. As jet technology matured, engineers refined compressors, introduced axial flow designs, and developed alloys capable of surviving extreme heat. Each generation of engines became more powerful, more efficient, and more reliable. What began as a desperate wartime experiment evolved into the backbone of global transportation. The jet engine became a universal standard, powering fighters, bombers, cargo aircraft, and eventually, the wide-body airliners that would carry millions across the planet every day. Its legacy is not confined to speed or altitude. The jet engine reshaped economies, altered warfare, and transformed cultural expectations of distance and time. It enabled global tourism, international business, and rapid humanitarian response. It made the world smaller, not by shrinking it, but by mastering the physics that once kept it vast. At its core, the jet engine represents the triumph of engineering over limitation. It is proof that when humanity confronts a boundary imposed by nature, the response is not surrender, but innovation. From fragile early turbines to the refined power plants of today, the jet engine stands as a monument to ingenuity, precision, and relentless ambition. The history of aviation is written not only in aluminum and steel, but in ideas bold enough to challenge the air itself. And few ideas have ever reshaped the world as profoundly as the jet engine. The early success of jet propulsion did not mean the problem was solved. On the contrary, it exposed an entirely new landscape of engineering challenges that had never existed in aviation before. The jet engine operated in temperature regimes that piston engineers had never needed to confront. Inside the combustion chamber, temperatures exceeded anything conventional aluminum alloys could survive. Turbine blades, rotating thousands of times per minute, were subjected simultaneously to extreme heat, centrifugal force, and corrosive exhaust gases. A single microscopic flaw could propagate into catastrophic failure within seconds. Airflow itself became an enemy, if not perfectly controlled. Compressors had to squeeze incoming air efficiently, without stalling, surging, or tearing themselves apart. Early centrifugal compressors were robust, but bulky, limiting engine scalability. Axial compressors promised far greater efficiency and compactness, but they were unforgiving. A minor imbalance in pressure or blade angle could cause a compressor stall, violently disrupting airflow and extinguishing combustion. Engineers were now designing machines where invisible air currents behaved as critically as solid metal. Material science became the decisive battlefield. New nickel-based superalloys were developed to withstand temperatures that would melt traditional metals. Cooling techniques were invented that bordered on counterintuitive engineering artistry. Turbine blades were drilled with microscopic channels, allowing cooler air to flow through their interiors, forming protective thermal barriers while still extracting energy from exhaust gases. These innovations did not emerge fully formed. They were born from repeated failure, from engines that destroyed themselves on test stands, from lessons written in scorched metal. The risks were not only technical. Jet engines consumed fuel at unprecedented rates. Early designs were powerful but inefficient, raising doubts about their viability outside military applications. Airlines questioned whether passengers would ever accept higher ticket prices in exchange for speed. Governments debated whether investing in jet technology was strategically wise or an expensive distraction. Entire industrial supply chains had to be reinvented, from precision machining to high-temperature testing facilities. Despite this, progress accelerated. Once engineers understood that jet propulsion favored altitude, a new design philosophy emerged. Aircraft were built to climb above weather systems, above turbulence, into thinner air where engines operated more efficiently and speeds could increase safely. Swept wings were introduced to delay the onset of shock waves near the speed of sound. Pressurized cabins became essential, transforming passenger comfort and safety while adding new structural demands to airframes. The moment jet-powered aircraft entered regular service, the paradigm of flight shifted permanently. Travel times collapsed. Routes that once required multiple refueling stops became non-stop journeys. The psychological distance between continents shrank. A business meeting, a diplomatic mission, or a family reunion could now occur across oceans without weeks of planning. Speed ceased to be a luxury and became an expectation. As jet engines evolved, so did their scale. Turbojets gave way to turbofans, which traded pure exhaust velocity for vastly improved efficiency. By accelerating a larger mass of air at lower speeds, turbofans reduced fuel consumption, noise, and operating costs. This single conceptual shift made mass air travel economically sustainable. The jet engine was no longer just a technological marvel. It was a commercial enabler. The socio-economic consequences were profound. Entire cities rose as global hubs, positioned not by geography alone, but by connectivity. Supply chains reorganized around air freight. Perishable goods crossed hemispheres overnight. Cultural exchange accelerated, not through abstract influence, but through physical movement of people. The jet engine quietly became one of the most powerful drivers of globalization in human history. Design legacies compounded over time. Lessons learned in military engines influenced civil aviation, while commercial demands pushed reliability standards that benefited defense applications. Redundancy, predictive maintenance, and modular engine architecture emerged from decades of operational data. Failures became rarer, not because engines were simple, but because complexity was mastered. By the late 20th century, jet engines achieved levels of reliability that early pioneers would have considered impossible. Millions of flight hours accumulated with astonishing safety records. Engines became quieter, cleaner, and more efficient, responding to environmental pressures and regulatory scrutiny. Yet the core principle remained unchanged from the earliest experiments: intake, compress, ignite, accelerate. The elegance of the idea endured because it was fundamentally sound. The jet engine's true legacy lies not in any single aircraft, but in the ecosystem it created. It forced engineers to think in systems rather than components, to consider airflow, heat, materials, and economics as inseparable variables. It demonstrated that engineering progress is not linear, but exponential once foundational barriers are broken. In mastering jet propulsion, humanity did more than build faster aircraft. It redefined its relationship with distance, time, and possibility. The engine that began as an answer to a mechanical limitation became a symbol of what happens when ambition meets discipline, when theory is forged into hardware, and when failure is treated not as an endpoint, but as data. The sky did not change. Humanity did. When jet propulsion crossed the threshold from experimental promise to operational reality, aviation entered a transformation so abrupt that entire fleets became obsolete almost overnight. The first operational jet aircraft did not simply improve on existing performance metrics. They shattered the assumptions that had governed aircraft design since the dawn of flight. Speed, once constrained by propeller physics, surged forward. Climb rates multiplied. Service ceilings climbed into altitudes where piston engines gasped for air, and mechanical limits, once thought absolute, dissolved under new principles. The first jet-powered flights revealed a startling truth. The atmosphere itself behaved differently when approached at these speeds and altitudes. Pilots found themselves above weather systems, flying through calmer, thinner air, where drag was reduced, and consistency replaced turbulence. For engineers, this revelation forced a reckoning. Aircraft were no longer bound to low-altitude compromises. Flight could now be optimized for a new vertical dimension, fundamentally changing how airplanes were conceived, built, and operated. As speeds approached the transonic regime, new challenges emerged that no previous generation had faced. Shock waves formed along wings and fuselages, producing sudden increases in drag and destabilizing control forces. Aircraft that were aerodynamically stable at lower speeds became unpredictable near the speed of sound. The response was not a single innovation, but a cascade of breakthroughs. Swept wings delayed compressibility effects. Area-ruled fuselages reduced drag spikes. Control surfaces were redesigned to maintain authority in previously unreachable flight envelopes. The jet engine did not exist in isolation. It forced an ecosystem-wide evolution of aerospace engineering. The introduction of jet propulsion into commercial service marked one of the most profound shifts in human transportation history. When airlines deployed their first jet airliners, the change was immediate and unmistakable. Routes that once required multiple stops, overnight rests, and complex logistics were transformed into direct, scheduled flights. Transcontinental journeys compressed from days into hours. Transoceanic travel became routine rather than exceptional. The world's geography did not change, but humanity's experience of it did. Quantifiable impacts followed rapidly. Average cruise speeds increased by hundreds of miles per hour. Aircraft utilization rates rose as faster turnarounds allowed more daily flights per airframe. Passenger capacity scaled upward as jet-powered aircraft enabled larger fuselages and higher lift-to-drag efficiencies. Ticket pricing models evolved as operating costs per seat mile dropped with each successive engine generation. What had once been a privilege of the wealthy began its transformation into a mass transportation system. Passenger experience evolved alongside performance. Pressurized cabins allowed flight at altitudes where oxygen levels would otherwise be lethal. Noise and vibration profiles improved dramatically compared to large piston engines, changing the sensory character of flight. The aircraft cabin became a controlled environment rather than a mechanical extension of the outside air. This reliability reshaped public perception. Flying ceased to feel experimental. It became dependable, repeatable, and increasingly trusted. Behind these visible changes lay an invisible industrial revolution. Jet engines demanded precision manufacturing at scales previously reserved for laboratory instrumentation. Tolerances shrank. Quality assurance expanded into entire disciplines, dedicated to fatigue analysis, thermal stress modeling, and failure prediction. Entire supply chains restructured around the production of high-temperature alloys, advanced bearings, and precision-machined compressor stages. Nations that mastered jet engine manufacturing gained not only aviation capability, but long-term industrial leverage. The military implications were equally transformative. Jet-powered fighters redefined air superiority. Speed became a decisive tactical advantage. Interceptors could respond faster, engage higher, and disengage at will. Bombers gained unprecedented reach, altering strategic doctrines and reshaping global deterrence. Reconnaissance aircraft operated above hostile defenses, gathering intelligence with reduced vulnerability. The jet engine compressed reaction times, shortened decision cycles, and reshaped geopolitical balance. As jet propulsion matured, its limitations became clearer and solvable. Early turbojets delivered extraordinary speed, but at high fuel costs and punishing noise levels. Engineers recognized that raw exhaust velocity was not. With turbofans, the jet engine crossed another threshold. Long-haul air travel became economically viable on a global scale. Wide-body aircraft emerged, capable of carrying hundreds of passengers across oceans non-stop. Air freight expanded into a pillar of global logistics, moving high-value and time-sensitive goods between continents overnight. Supply chains reorganized around air connectivity, reshaping manufacturing, retail, and distribution worldwide. Each generation of jet engines incorporated lessons accumulated over millions of flight hours. Compressor designs improved, combustion efficiency increased, and material science advanced to tolerate ever higher operating temperatures. Digital engine control systems replaced mechanical governors, enabling precise fuel management and real-time performance optimization. Engines began to monitor themselves, detecting anomalies before they escalated into failures. Reliability statistics reached levels that transformed aviation safety from aspiration into expectation. These advances influenced engineering philosophy far beyond aviation. The jet engine taught designers to think in systems rather than components, to model interactions between airflow, heat, stress, and economics as a single equation. Failure was no longer treated as an anomaly, but as a predictable event to be managed, mitigated, and contained. Redundancy, graceful degradation, and probabilistic safety analysis became standard practices, spreading into power generation, automotive engineering, and industrial design. Culturally, the jet engine became a defining symbol of the modern era. It represented speed, ambition, and the promise of connection. Airports evolved into global crossroads, reshaping cities and regional economies. Tourism expanded beyond borders once considered unreachable. International business accelerated, not because communication improved, but because physical presence became feasible at unprecedented speed. The jet engine did not merely carry passengers. It carried ideas, culture, and influence across the planet. Despite its complexity, the jet engine's core principle remained unchanged from its earliest conception. Air is drawn in, compressed, mixed with fuel, ignited and expelled to produce thrust. Around this simple cycle, generations of engineers layered sophistication, efficiency, and resilience. The enduring power of the jet engine lies in this balance between conceptual elegance and engineering mastery. By the time jet propulsion became the default mode of flight, it was no longer perceived as revolutionary. It had become infrastructure, silent, dependable, and essential. Passengers no longer marveled at the engines beneath the wings, yet their lives were structured around the possibilities those engines enabled. Distance lost its authority, time bent to technology. In redefining flight, the jet engine redefined the world itself. As jet propulsion became the unquestioned foundation of modern aviation, its true influence began to reveal itself not in a single aircraft or era, but in the long arc of adaptation, refinement, and inheritance that followed. The jet engine did not reach a final form. It evolved continuously, absorbing lessons from every flight hour, every failure analysis, and every economic pressure imposed by a changing world. Its legacy is not static hardware, but a living design philosophy that reshaped how engineers think about performance, efficiency, and endurance. One of the most decisive shifts in this evolution was the move away from pure speed as the primary objective. Early jet aircraft were designed to go faster than anything before them, often at the expense of range, efficiency, and longevity. As civil aviation expanded, these priorities reversed. Airlines demanded engines that could operate reliably for thousands of hours between overhauls, consume less fuel, and meet increasingly strict noise and environmental regulations. This pressure forced engineers to reframe success. Maximum thrust became less important than sustained economical performance. The turbofan engine emerged as the defining response to this new reality. By diverting a large portion of airflow around the engine core, turbofans dramatically increased propulsive efficiency. Instead of expelling a narrow jet of extremely fast exhaust, they moved a greater mass of air more gently. The result was quieter operation, lower fuel burn, and greater range. This concept proved so effective that it became the dominant propulsion architecture for commercial aviation, a status it retains to this day. Military aviation followed a parallel but distinct path. While efficiency mattered, performance and adaptability remained paramount. Variable cycle engines were explored, capable of shifting characteristics between. As engines grew more sophisticated, materials science became inseparable from propulsion design. Advances in metallurgy enabled higher operating temperatures, directly translating into improved efficiency. Single crystal turbine blades eliminated grain boundaries that once limited durability. Ceramic matrix composites entered high heat sections, reducing weight while tolerating temperatures that metals could not survive. These materials did not merely improve engines incrementally, they expanded the feasible design space, allowing engineers to pursue configurations that were previously impossible. Equally transformative was the rise of digital control. Full authority. Digital engine control systems replaced mechanical linkages and analog regulators, allowing engines to respond dynamically to changing conditions. Fuel flow, compressor geometry, and turbine behavior could now be optimized in real time, balancing performance with longevity. This digital nervous system reduced pilot workload, enhanced safety, and enabled predictive maintenance. Engines began to generate data as valuable as thrust, feeding continuous improvement loops that refined future designs. The influence of jet engine evolution extended beyond aviation into energy production and industrial engineering. Gas turbines derived from aviation engines became central to power generation, particularly in combined cycle plants, where efficiency approached theoretical limits. The same principles that propelled aircraft across continents now powered cities and industries, illustrating how aviation innovation often radiates outward into broader technological ecosystems. Culturally, the jet engine's presence became so ubiquitous that it faded into the background of everyday life. Millions of people crossed oceans without considering the complexity beneath their feet. Yet this invisibility is itself a testament to success. Technologies that truly integrate into society cease to feel extraordinary. They become assumptions. The jet engine turned global mobility from a spectacle into infrastructure. Environmental considerations introduced new constraints that further shaped engine evolution. As aviation scale grew, so did scrutiny of its emissions and noise footprint. Engineers responded with incremental but meaningful gains. Higher bypass ratios, improved combustion efficiency, and advanced acoustic treatments. While the jet engine remains an energy-intensive technology, its trajectory reflects a continual effort to reconcile human mobility with planetary limits. Design influence also flowed backward through time. Modern engines informed reinterpretations of older concepts. Lessons learned from decades of turbofan operation reshaped how engineers approached future propulsion systems, including open rotor designs, hybrid electric assistance, and sustainable aviation fuels. Even as new ideas emerged, they were evaluated against the benchmarks set by the jet engine's reliability, scalability, and proven performance. The jet engine's legacy is also institutional. It forced unprecedented collaboration between governments, manufacturers, airlines, and regulators. Safety standards evolved in response to its complexity. Certification processes became more rigorous, data-driven, and global in scope. International cooperation expanded as engines built in one country, powered aircraft operated worldwide. This interdependence mirrored the connectivity the engines themselves enabled. Perhaps the most enduring influence lies in mindset. Jet propulsion taught engineers that breakthroughs are rarely singular moments. They are cumulative processes shaped by persistence, iteration, and the willingness to fail intelligently. Early engines were crude and unreliable, yet they were not abandoned. Instead, each failure became a data point, each limitation an invitation to innovate. This philosophy now underpins aerospace engineering at every level. As the jet engine matured, it became both a foundation and a springboard. New aircraft designs assumed its presence, freeing designers to focus on aerodynamics, structures, and systems integration. Entire generations grew up in a world where crossing hemispheres in a single day was normal. The engine's success reshaped expectations not only of flight, but of progress itself. In this way, the jet engine transcended its role as a machine. It became a template for how humanity confronts complex challenges. Identify the constraint. Rethink the fundamentals. Accept risk. Iterate relentlessly. Scale responsibly. Few technologies illustrate this process as clearly or as consequentially. What began as a solution to a mechanical limitation evolved into one of the most influential engineering achievements in history. Its echoes are found in every modern airport, every global supply chain, and every moment when distance is no longer an obstacle, but a variable to be managed. The jet engine's influence is not measured solely in thrust or speed, but in the altered rhythm of the world it helped create. In the end, the story of the jet engine is not merely a chapter in aviation history. It is a statement about human ambition and the willingness to challenge limits that once appeared absolute. What began as a response to a technical ceiling imposed by propellers evolved into a force that reshaped how the world functions, how societies interact, and how humanity understands distance itself. The jet engine succeeded because it addressed more than speed. It solved a systemic problem. It reconciled physics, materials, and human need into a single, repeatable solution. By doing so, it transformed flight from a mechanical struggle into an engineered equilibrium, where thrust, airflow, and structure operate in harmony. This balance did not emerge instantly. It was forged through decades of refinement, setbacks, and recalibration. Each generation of engineers inherited both the achievements and the shortcomings of those before them, pushing the design forward without discarding its core principles. The lasting lesson of jet propulsion lies in its adaptability. The fundamental thermodynamic cycle remains unchanged, yet its execution has been endlessly refined. Engines grew quieter as societies demanded less noise. They became more efficient as fuel costs and environmental concerns rose. They became more reliable as aviation shifted from novelty to necessity. Few technologies have demonstrated such resilience under evolving constraints. The jet engine did not resist change. It absorbed it. Its impact on global society is difficult to overstate. Entire economic models depend on the assumption that people and goods can move across continents within hours. International collaboration, modern tourism, just-in-time manufacturing, and globalized education all rely, directly or indirectly, on jet-powered flight. The engine enabled not just mobility, but predictability. Schedules became trustworthy. Borders became permeable. Opportunity expanded beyond geography. From a strategic perspective, the jet engine altered how nations perceive security and influence. Airspace became a domain of speed and reach, rather than endurance alone. Deterrence strategies, humanitarian response, and global diplomacy all adapted to a world where rapid aerial access was assumed. The compression of time introduced by jet propulsion reshaped decision-making at the highest levels of power. Yet the jet engine's greatest contribution may be philosophical. It demonstrated that transformative progress rarely comes from perfect conditions. Early jet engines were inefficient, fragile, and unreliable. They survived not because they were flawless, but because their potential was unmistakable. Investment continued despite failures. Engineers persisted despite skepticism. This persistence, grounded in rigorous analysis rather than blind optimism, became the engine's true fuel. Modern aviation now stands at another inflection point. Environmental pressures, sustainability goals, and emerging propulsion concepts challenge the dominance of traditional jet engines. Hybrid systems, alternative fuels, and new architectures are being explored. Yet every proposed successor is measured against the benchmark the jet engine established. Reliability, scalability, and global integration remain non-negotiable standards. Any future propulsion system must match not only the jet engine's performance, but its capacity to reshape society. This continuity underscores a critical truth. Technological revolutions do not end when a solution becomes widespread. They enter a new phase, one of stewardship and evolution. The jet engine's future may look different from its past, but its legacy will persist in the principles it established. Disciplined engineering, systemic thinking, and the courage to rethink fundamentals. Looking back, the jet engine unified the world not through ideology or policy, but through physics. It connected distant cultures by making proximity achievable. It aligned economies by reducing the cost of distance. It altered human perception by turning the extraordinary into the routine. These changes were not imposed. They emerged naturally from a machine that worked, scaled, and endured. The engine itself remains largely unseen, hidden beneath wings and within nacelles, rarely noticed by those whose lives it accelerates. This invisibility is the mark of true integration. When technology disappears into daily life, it has succeeded beyond spectacle. The jet engine no longer demands attention. It delivers expectation. And yet, behind that quiet reliability lies one of the most ambitious engineering endeavors ever undertaken. A machine that operates at extreme temperatures, tolerates immense forces, and performs flawlessly thousands of times each day. A machine born from theory, hardened by failure, and perfected through iteration. A machine that changed how humanity moves, thinks, and plans. The history of aviation is not a sequence of isolated inventions. It is a continuum of bold decisions layered upon one another. The jet engine stands at the center of that continuum, not as an endpoint, but as a foundation. It reminds us that progress is achieved not by avoiding limits, but by confronting them directly. In the arc of human innovation, few technologies have carried such weight. Fewer still have done so with such quiet consistency. The jet engine did not just power aircraft. It powered a transformation of the world's tempo. The history of aviation is written with steel, ingenuity, and the will to challenge limits.